Today we're going to be talking a little bit about graphing quadratic functions. Now this is more of a focus in the class college algebra than it is in the class intermediate algebra, but we still do introduce the concepts of how you graph a quadratic and what quadratics look like. Now a function of the form x squared, or y equals x squared I should say, always has this basic u or parabola shape. If the leading coefficient in front of the x squared is positive, this thing will be facing up such that whenever you plug in larger x's, you end up with larger y's in terms of being more positive. Versus if the leading coefficient in front of the x squared is negative, it will be facing down. And that's one of the most fundamental parts of talking about how to graph a parabola, is that you want to think about, does it open up or does it open down? How do you know something will look like a parabola? It will always take the form of having an x squared be the highest part of the polynomial, aka it will always be a polynomial of degree 2. It may also have an x term, it may also have a constant. That x could be multiplied by something, so it could take the form y equals, I don't know, negative 7x squared plus 10x minus 2. Why not? Don't know exactly how that looks, but you know it's going to be an upside down U shape because of that leading coefficient and the fact that it's an x squared, indicating that it's a polynomial of degree 2. When we're talking about the anatomy of a parabola, there's a couple of different components that we really want to zero in on. First of all, in addition to being called upside down or right side up, upside down being a U looking upside down, right side up looking properly like a U, a very key point we always want to discuss is called the vertex, which is either the highest or lowest point of the parabola. So the vertex is your highest or lowest point. If it's right side up, it's your lowest point, it's a minimum value. If it's upside down, it's your maximum point, it's your highest value. We can imagine drawing a perfectly straight line through that highest or lowest point, and we would notice that the parabola is perfectly symmetric on both sides of that straight line. It's going to be kind of going the same distance away. So like if there was a point, let's say hypothetically, this point that was your vertex was at, let's say, negative 2, 10. Why not? If there was a point over here at negative 1, 8, where we basically went over to the right 1 and then down 2, there would be symmetrically a point over here at negative 3, 8, that whenever we go over 1 in the other direction, we'd still go down 2 from that vertex. That's really what that means, is that there's this nice, beautiful symmetry going on that graph. So whenever you're writing the axis of symmetry, what that is asking you to do is write the vertical line that goes through the vertex. And it's always going to take the form x equals h, where h is the x value of the vertex. How do you find the x value of the vertex? Well, there is the formula x is equal to negative b over 2a. This comes actually from the process of completing the square. If you're curious about that, I would recommend kind of Googling it. There's a beautiful proof about that. But the short of it is that the x coordinate of the vertex will always be at negative b over 2a in terms of the equation, where b is the number attached to your x, while a is the coefficient attached to the x squared. In order to find the y value of the vertex, you're just encouraged to go ahead and plug in that point. So just as a bit of a summary, the vertex is going to be your highest or lowest point of the parabola. It's sometimes also called a turning point because it's where you go from increasing to decreasing or from decreasing to increasing. But that will always be your vertex. The axis of symmetry is the line that goes through that vertex, so the parabola is symmetric on both sides of that line. The x-intercept and y-intercept, these are concepts that we've seen before. So wherever your parabola physically crosses the y-axis, that's still your y-intercept. How are you going to find that? Well, if he's crossed the y-axis, he hasn't moved left or right, so that means x is 0. Versus your x-intercepts, if they exist, they don't always exist. There's always a y-intercept and there's sometimes an x-intercept. That's going to be where you cross the x-axis, and you want to solve for when y is 0 to look for that. How could you possibly not have an x-intercept sometimes? Well, sometimes your parabola will be physically located so far away from the x-axis, and it will be facing a direction such that it never crosses it, and in that case you won't have an x-intercept. If you're solving and it's a case where there's not an x-intercept, you might have something along the lines of an equation is x squared plus 50, and you would try to solve for the x-intercept by setting that equal to 0. You would subtract 50 from both sides, and then you would undo that square with a square root, and you'd be like, oh my gosh, I'm square rooting a negative. That would mean there is no x-intercept, because you're trying to square root a negative, and that's not allowed in the real numbers. So if you're going to plot a quadratic, there's several different components that you want to identify. You want to identify your vertex, which is found using x is negative b over 2a, and then you plug that value in to find the y-coordinate. You want to plot that vertex. You want to find the y-intercept by plugging in x is 0. And then you want to choose some x values on either side of the vertex to plug into the equation in order to solve and find some other points. Plot them, and then you're going to label your axis of symmetry will always be x is h, which is your x-coordinate of the vertex. So let's take a look at some examples here. So if you're given a parabola, you can identify all of the key parts of it. So before I go through it, I'm actually going to encourage you to go ahead and try to find these key parts yourself. So we're looking for the vertex, we're looking for the axis of symmetry, we're looking for any y-intercepts, we're looking for any x-intercepts, we're also looking for the domain and the range. And there's an understanding on this graph that there are arrows up here that are making this go up towards positive infinity. So go ahead and pause your video, see if you can find these things, and then we'll compare. So the vertex, that's going to be your highest or lowest point. So in this case, that would be this point down here at 3, negative 3. That would be your vertex. So you're always going to be looking for that minimum or maximum to find your vertex. For the axis of symmetry, that is going to be the perfectly straight line that goes through that vertex, and the way that we write perfectly vertical lines is x equals, and in this case that x-coordinate is 3, aka that x-coordinate of the vertex. For the y-intercepts, we want to physically look at where this crosses the y-axis, which is at the point 0, 6. Sometimes people will just list that y-intercept as 6, but really the proper point is the point 0, 6. For the x-intercepts, those look like those are a little bit hard to tell the exact coordinates of. So I would say they look like they're approximately at around 1, and I would say maybe 1/3, 0. And then approximately, I would say probably about 4 2/3, 0. Chances are on any sort of practice of this, you would actually have a way to be able to tell those exact coordinates. In this particular example, you can't, just because if that's the way that the graph worked out, but those approximate coordinates are labeled there. As for the domain, while we have 2 arrows going in both directions, forever to the left and forever to the right, so that would be going from negative infinity to positive infinity. And for the range, he's going forever upwards, but he stops at that minimum value, which is the vertex. So in terms of the range, we go down to negative 3 and then continue going up to positive infinity forever, because again, we're looking up and down, so we're just paying attention to that y-coordinate. As for whether or not this opens upwards or downwards, this in particular is opening upwards. So we would expect that leading coefficient of a to be greater than 0. He would have to be positive to make him open upwards like this. So now let's say you're working the other way around. So you're given the equation, in this case f of x is equal to 2x squared plus 1. And we want to graph him, and then we need to also find all of these important points on here. So let's go ahead and do that. And we're also looking for the domain and range. So first of all, do we expect him to open upwards or downwards? Because that leading coefficient a is greater than 0, we're going to expect him to open upwards. Then I would first encourage you to go ahead and find the vertex, because that's really a key point that you need to find. For the vertex here, that's negative b over 2a. In this equation, we're given that a is 2. There is no plane x term, so that means b is 0, and c is 1. So when we're plugging in here to find the x-coordinate of the vertex, that would be negative 0 over 2 times 2, which just comes out to 0. So the x-coordinate of the vertex is 0, and that means that we've also just figured out that the axis of symmetry will be at x equals 0. So I'm actually going to even go ahead and draw that beautiful axis of symmetry. To find the y-coordinate of the vertex, you have to plug 0 back in. So if I evaluate the function f at 0, that means I'm doing 2 times 0 squared plus 1. 0 squared is 0, 2 times 0 is still 0, so we're left with 1. So the y-coordinate is 1. So at 0, 1, we have ourselves the vertex. Now we're wanting to look for the intercepts. So we actually coincidentally already found the intercept. So not only is the vertex 0, 1, but that also happens to be your y-intercept, because the y-intercept occurs wherever you cross the y-axis, and it occurs where x is 0, tomato, tomato. In this case, that's what we already found. Now we're going to look to see if there are any x-intercepts. We should already actually be predicting they're not. Why is that? Well, because our y-intercept's up here, and we know this guy's going to open upwards. But we can also confirm that by actually plugging into the equation. So the equation is f of x is equal to 2x squared plus 1. If we were, remember f of x is another term for y, so if we were to plug in y is 0 and solve for x, well, I would first subtract 1, subtract 1. Negative 1 is 2x squared, divide by 2, divide by 2. Negative 1/2 is x squared. And then when I take the square root, I cannot square root a negative. So there are no x-intercepts for that reason as well. Now I want to find a few more points to plot. So I'm going to go ahead and just make myself an xy table. So we have x, and we have that f of x is equal to 2x squared plus 1. And what I would recommend doing consistently on your table is go ahead and put your vertex in the center here at 0, 1. If I had some y-intercepts, I might put that in the table as well. And then I want to plug in a couple of x values to the left and to the right of my vertex and see where they're going to be. So if I plug in negative 1, for example, negative 1 squared is going to give us 1. 2 times 1 plus 1, 2 times 1 is 2, plus 1 will give us 3. So we also have a point at negative 1, 1, 2, 3. And the way the axis of symmetry works, I should actually predict the point that is in the same distance away from the vertex on the other side should actually work out the same, which I can confirm now. So if I do positive 1 squared, that still gets me 1 times 2 is 2, plus 1 is also 3. So I also have a point at 1, 3. And then I'm also going to just emphasize that original point at 0, 1. Now we're going to plug in some more points. So if I plug in negative 2, for example, negative 2 all squared, it gets me 4 times 2 is 8 plus 1 is 9. So I've got a point here at negative 2, 9. And then as a last point, if I plug in positive 2 all squared gets me 4 times 2 is 8 plus 1 is also 9. So I'm going to have another point at 2, 9. And then when I connect them, that will make our nice, beautiful parabola shape. So just to recap on that, you want to first plot your vertex, And then you want to choose some x values to the left and to the right of that vertex so that you get your full shape. Had I only picked values to the right, I would have only had half of my shape, and that would have been no good. And as you become more comfortable with how the axis of symmetry works, you'll also save yourself some time because you'll notice that those y values repeat. Now we also need to note what the domain and the range is, and that's best noted from the graph itself. So left to right, I go forever to the left, forever to the right. That means its domain is all real numbers, aka negative infinity to infinity. For the range, I go forever up, but then I stop at my vertex, and the y-coordinate on my vertex is 1. So he goes from positive 1 all the way up to positive infinity. And recall on those infinities, I always use parentheses because I don't reach them, while that vertex gets a bracket because I do. Let's go ahead and try this next one. So we're going to do a similar process. So we want to identify the vertex, axis of symmetry, any intercepts that might be occurring, and then we also want to give the domain and range. Also, before we go too far, we want to go ahead and predict, should this be right side up or upside down? He should be upside down, because a, which is -1, is less than 0. So we're already predicting this should be an upside down parabola. I'm going to encourage you to go ahead and pause your video and try to find all these about your quadratic here, and then we'll go over it together. So let's start with the vertex. So for the x-coordinate of the vertex, that's going to be -b over 2a. I might want to identify what my a, b, and c are. A is -1, b is 4, c is -7. So -b over 2a is going to be -4 over 2 times -1. -4 over -2, which gets me +2. So I've just confirmed the x-coordinate of my vertex is +2. And that means I've already found my axis of symmetry, which will be x equals +2, which I can go ahead and graph as well. So I'm going to expect that my equation, or my parabola, is perfectly symmetric across this line, x equals 2. Now I'm also going to go ahead and plug that into my equation. So y will equal -2 squared plus 4 times 2 minus 7. I'm actually going to move the words for the axis of symmetry over a little bit, just so that we have a little bit more room here. So keep in mind, in terms of order of operations, this negative chilling out front is actually a -1 times what's going to happen with the squaring. That negative is not inside the parentheses. And 2 squared gets us 4, plus 4 times 2 is 8, minus 7. And then we want to keep on going. -1 times +4 is -4, plus 8 minus 7. -4 plus 8 will give us +4. +4 minus 7 is -3. So the y-coordinate on that vertex is -3. So I'm going to go ahead and put a point at 2, -3. And I'm expecting that that is my maximum value because I already am thinking this guy's going to be upside down. Now let's find some other pieces of information. So I want to find the y-intercept, and for the y-intercept you have to plug in x is 0. The reason why I didn't have to find that explicitly before is because my y-intercept actually was identical to my vertex. That's not the case here. So if I plug in x is 0, I'll get y is equal to -1 times 0 squared plus 4 times 0 minus 7. -1 times 0 squared is -1 times 0, that's just 0, plus 4 times 0 is 0, so you're left with -7. So your y-intercept is at the point 0, -7. So I can go ahead and plot 0, -7 down here. Now let's find the x-intercept. So for the x-intercept, you need to plug in y is 0. So on that original equation, that would look like 0 is equal to -x squared plus 4x minus 7. Now when you have a leading coefficient that is negative, I would strongly recommend for your first step solving for the x-intercept, go ahead and divide each and every term by -1. 0 divided by anything is still 0. -x squared divided by -1 leaves us with +x squared. Positive 4x divided by -1 leaves us with -4x. -7 divided by -1 leaves us with +7. Then I would want to see if this guy is factorable. If he's going to be factorable, there would have to be something that multiplies to positive 7 and adds to negative 4. There is not. You may also be predicting, just based on how the graph physically looks, that we're actually unlikely to go ahead and cross that x-axis, and you would be correct. But we can also confirm that by either solving by completing the square or using the quadratic formula. I'm just going to use the quadratic formula. So that would be x is the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. Then you want to tackle inside the square root first. So negative 4 all squared gets us 16. 4 times 1 times 7 gives us 28. 2 times 1 is 2. And then hopefully we're already starting to notice that square roots is going to have a negative in there, because 16 minus 28 gets us negative 12. So there is no real x-intercepts. So we're not going to have any x-intercepts. That would be none for the x-intercept. Sometimes it does work out where there's an x-intercept, and that's why we did all that work solving quadratic equations. Whenever you do solve this, and it's not trivial, so even up here, this would be a good example of where you would have solved it. It would have been not trivial, and it probably would have been some sort of result from a quadratic equation. And even though there's techniques that I actually from this graph could find out exactly where that x-intercept is, that's not really the point of this video. It's just going to approximate for now. That's fine. Versus down here, we can already see it's going to be upside down, not crossing that, no real x-intercepts. We're going to move on. Now let's go ahead and make our chart. So in your chart, you want to go ahead and center that at your vertex. In this case, it's at 2, negative 3. And then you want to plug in a few values to the left and to the right of that. So I'm going to plug in 1 and 0 and 3 and 4, because those are kind of the values that are near there. When x is 0, I actually already know, because I already found it, that y will be negative 7, because I already found that earlier. Now let's confirm for some other values. I'm probably also predicting based on how an axis of symmetry works, so that should be what I get when I plug in 4 as well. And recall that the actual equation is y equals negative x squared plus 4x minus 7. So if I plug in positive 1 here, 1 squared gets us 1, times negative 1 gets us negative 1. 4 times 1 gets us 4, minus 7. Negative 1 plus 4 is positive 3, minus 7 is going to get us negative 4. We should predict that when we plug in positive 3, we should end up getting a similar result. 3 squared gets us 9, times negative 1 is negative 9. 4 times 3 is 12, minus 7, negative 9 plus 12 also gets us positive 3, minus 7 is negative 4. So I just confirmed there's a point at 1, negative 4, and at 3, negative 4. When I plug in 4, I'm already predicting I should get negative 7 if the axis of symmetry is going to be behaving the way that I'm expecting. 4 squared gets us 16, times negative 1 is negative 16, 4 times 4 is 16, negative 16 plus 16 is 0, minus 7 is going to give us negative 7. So we're going to end up with a point at 4, negative 7 here for our final beautiful parabola. So just as a recap on how to graph these guys, what you always want to look for is your vertex slash axis of symmetry. That will always occur where the x-coordinate is negative b over 2a, and then you plug that in to find the y-coordinate. You're also going to look for any y-intercepts, which is where you set x equal to 0 and solve for y. That will always exist. For the x-intercepts, you set y equal to 0 and solve for x. That will sometimes exist and it sometimes won't. Then in order to finish graphing, what you're going to want to do is make a table of values that is centered at your vertex. Pick a couple x's to the left of that, pick a couple x's to the right of that. So that could happen to be at 0, or it could be at some other number. Again, center at the vertex, few x's to the left, few x's to the right. And if your axis of symmetry is correct, then you should see this pattern in your table where the y values are going to repeat in both directions. Then you can graph your nice beautiful parabola. you should double check that he's upside down if that leading coefficient is negative, and that he is right side up if that leading coefficient is positive. You also shouldn't forget to find the domain and range like I should have remembered to do here, so let's go ahead and do that from our graph here. So for the domain here, he's going forever to the left and forever to the right, so that would be from negative infinity to infinity. For the range, he goes forever down, but in terms of up and down, he stops with a maximum at -3. So he goes forever to the left, comma, and then has a maximum at -3 with a bracket to indicate that I do hit -3 itself, because there for that range you're focusing in on those y values. And so for the domain and range, I would always answer that last based on how the graph itself physically looks.